SwayamPrabha. Digital India. Educated India.
Dear learners, greetings from IIT Guwahati. We are in the MOOCs course Power Plant System Engineering, Module 3, Gas Turbines and Combined Power System. So, in the last few lectures, we have given emphasis for different types of gas turbine cycles, and with appropriate modifications, the ideal gas cycle, which is supposed to be a Brayton cycle, gets modified to variety forms, which we call it them as regeneration, reheat in the turbines, compressor intercoolings. So, those modifications helps us in improving the power output and cycle efficiency. So, another significant aspect of this gas turbine cycles, in fact, the gas turbine cycle is the most versatile cycle which can be integrated to any kind of other power generating systems. So, such cycles are known as combined power cycles. So, in these lectures, we will try to see or emphasize few such combined modes in which gas turbine cycles can be coupled, and so that they form a combined cycle power plants. And towards the end, when you look at the combination of two different concepts, like combination of steam with gas, combination of nuclear power plant with gas turbine power plants. So, there has to be some basic minimum justifications to work them in combined mode. For such cases, energy and exergy analysis is very vital. So, basically when we are combining them, we are essentially increasing the infrastructure, capital cost and complexity of the systems. But that has to be justified with the need of technical requirement. So, one such thing is that we need to do energy auditing, we also need to do the exergy analysis. So, what does these two concepts gives us? It gives the fact that each mode of operations, like either you go for steam turbine mode and gas turbine mode, they will have their individual limitations and individual capability of operating to in the operating limits. But when you combine them, so there has to be some justifications that cycle efficiency should improve, work output should be improved. So, such things is possible if you do a comprehensive energy and exergy analysis. So, in this lecture we will provide a case study in which a gas turbine cycle is combined with a steam power cycle. So, let me start with the first thing, that what we have already understood, that the idea of combined cycle has shown interest with the need to improve the Brayton cycle efficiency by utilizing waste heat from the exhaust gas. So, that is the entire idea. For that reasons, we intentionally make this Brayton cycle to a non-ideal mode by introducing regenerators to improve cycle efficiency, but of course, it does not increase the power output, and through that mode the optimum pressure ratio for maximum efficiency improves sharply with low value of regeneration, resulting in the reduction of power. So, first thing, it improves the optimum pressure ratio, but it lowers the power. That means, if you look at this particular figure, simple cycle and non-ideal cycle, although optimum pressure ratio, that means shifts towards left, but what we see is that the after the peak efficiency, the cycle efficiency drops when you increase the pressure ratio. So, this is the disadvantage of regenerator while when integrated with a Brayton cycle to operate in a non-ideal mode. Another requirement is that the simple cycles normally operates in the maximum power situations, whereas the regenerative cycles becomes meaningful when it is operated in near cycle efficiency. That means, when you add complexity in this to the systems by introducing a regenerator, then we must operate it in this range, in the maximum temperature range. Then only the justification of heat exchanger regenerator seems to be appropriate. So, this was the concept what we understood for the gas turbine cycles when they operate in their own individual mode. But what happens that in some situations, if you want to improve the efficiency or power of a gas turbine systems, other possible way we can do it, that we can integrate with the other power generating unit. So, one of the method or thermodynamic method is to use large quantity of energy that leaves from the turbine exhaust to generate steam in a steam power plant. So, what happens is that normally we say that heat exchanger is one way that gas turbines are operated in non-ideal mode. So, that we call them at a heat exchange cycle. But again, instead of heat exchanger, we think that the exhaust from the gas turbine can be directly coupled to provide necessary heat input for a steam power systems. So, that is the benchmark applications, that when we move from gas turbine cycle operations from individual mode to combined mode. So, if you look at the realistic numbers, what we understood is that the gas turbine power plants use high temperature machines, and in this case it is turbine, and where we look at the maximum temperatures in the range of 1000, 1100, 1200 to 2000 degree centigrades. But if you look at similar numbers in steam turbines, they normally operate in superheated mode at high pressure in the range 550 to 1200 degree centigrades. So, it becomes a natural solution that the exhaust temperature that comes out from a gas turbine unit is in much higher side. So, that exhaust gas can be used to provide necessary heat input to the steam power systems, because of this application viewpoint of steam and gas turbine unit operations. So, it becomes a natural solutions for the both units like steam and gas, that they can be combined, one with hot end, that means gas turbines in the hot end and steam turbines in the cold end. So, that we call them as a combined cycle power plant. But however, such combination has a disadvantage, that it increases the complexity, and second, essence of combining both technology from one power plant complex. So, there has to be some synchronization between the gas turbine units and steam turbine units. But however, the combined cycles have high efficiency over wide range of loads. They are suitable for both base loads and cyclic operations. They have a flexibility with quick starting. So, in case steam turbine does not work, so necessary power can be achieved from gas turbines, and instead in some cases we require a peak load requirement, where both the units can work combinedly to inflate the load requirement. So, these are the some basic advantages. So, people have looked into different modes of combined cycle operations. So, there are some workable operations, what we call as heat recovery boiler systems, that can be with or without supplementary firing. Other can be heat recovery boiler with regeneration and feed water heating. Then heat recovery boiler with multiplexer steam cycle, and closed cycle gas turbine with steam cycle feed water heating. But however, there are, in addition to this, there are many other possibilities, but in this lecture we will just demonstrate few concepts of gas turbine cycles, which is normally integrated with a steam power unit. So, first we call this as a heat recovery boiler. So, typically heat recovery boiler is normally used for steam turbine unit or other appropriate name is the steam generator. So, what we are looking at here is that, so instead of devising a extra boiler or steam generator for steam power systems, we look into another mode of technology and we call it as a heat recovery boiler. So, what is the role? That this heat recovery boiler will have same entities which is normally a steam turbine unit has. So, this heat recovery boiler will have a superheated region, will have a conventional steam drum or boiler regions, will have also economizer regions. So, this is the typically a steam generator unit of a steam turbine has, but we will have the similar features, but how it is needs to be operated? This needs to be powered from the exhaust of the gas turbine unit. Normally, exhaust of the gas turbine unit is at very high temperatures. So, those temperatures can be utilized at various locations, either superheater, boiler or economizer unit to generate steam. So, basically it is a heat exchanger and that increases the temperature of the steam. So, instead of adding extra fuel from the coal fired unit or any other unit, we are just taking it from the gas turbine unit itself. But in some cases we can have a extra or add on supplementary firing unit where extra fuel can be added. So, these two things will combinedly power the heat recovery boiler unit, and this heat recovery boiler unit provides necessary steam to the steam turbine, that again expands in the steam turbine. So, basic idea between these two units is that the integration point between these two. So, this part is your gas turbine unit, this part is your steam turbine unit, that is lower part is your steam turbine unit, and each one is generating power. So, W gas, and steam turbine also gives the power. So, combined power can be used to give the necessary power conversion through the generator. So, since entire resources comes from the gas turbine units, so the gas turbine units are operated with a very high fuel ratio, 400% of theoretical air. And additionally, when efficiency is of prime importance, separate supplementary firing unit is integrated with heat recovery boiler. So, basically these two units are essential addition for a combined cycle mode of operation. And with similar analogy, we can think of a coal gasifier based combined power cycle. So, here what we have here is that here you have, there are three basic unit. One is gasifier unit, and that gasifier units normally handles coal. So, these coals can be of low, medium or high calorific value fuels. So, the coal can be of low grade coal or high grade coal. So, essentially whatever the nature of the coal, we get a gas which is derived from any source of fuel, that is gasifier unit. Second part what we have is the gas turbine units. So, connecting point between this gas turbine unit and the gasifier unit is the gas to gas heat exchanger, and that provides necessary gas to the combustion chamber. And then from this combustion chamber it goes to the gas turbine units. So, this gives the power requirement from the gas turbine unit, and exhaust from the gas turbine unit again goes to heat recovery steam generator. This is something similar to heat recovery boiler unit in our previous discussions. So, heat recovery steam generator. So, that gas is essentially powers the steam turbine unit, and this has essentially has superheater unit, reheater unit or economizer unit, all the things are integrated here. So, here we get steam power output from the steam turbine unit, and power productions can happen from the gas turbine unit and from the steam turbine unit. So, essentially this is a combined cycle mode of operations and which integrates coal gasifier unit with a steam and gas turbine systems. So, advantage is that we can use synthetic fuel or we can use liquid fuels. We can also use many gas mixture, low, medium, high calorific gas, and also attractive utilization is that low calorific gases for electric generations, which normally is not possible if it has to be handled by any single unit. So, as a benchmark here I have given some numbers where a coal gasifier combined cycle power plant operates. This is a realistic picture or number in which it is told that the temperature and pressure limits for gas turbine units is 9 bar and 980 degree centigrades. Steam turbine units operates in the range 20 bar and 480 degree centigrades, and they have overall efficiency of 35 to 45%. The workflow or working fluid flow has been shown from this thermal circuit diagrams. So, it starts with 1 and ends with 20, and finally, till we extract maximum possible energy from the products that goes out from the unit, we can reutilize it at various locations. So, this is the essential objective of this combined cycle power plant mode, and this is a very good workable model, and it has already been implemented at various locations. So, what extra unit that gets added here is the heat recovery steam generator unit, which is this. Another is gas to gas heat exchanger, that is the connecting point between the coal gasifier unit and gas turbine unit, and the connecting point between gas turbine unit and steam turbine unit is the heat recovery steam generator. The next application for combined power cycle operation is integration with a nuclear power plant. So, normally when you think about a nuclear power plant, we call this as a reactor. So, we call this as a high temperature gas cooled reactor. So, that is nothing but your number 3. So, this unit we call it as a high temperature gas cooled reactor, and here we look a closed gas turbine cycle. So, in this closed gas turbine cycle, your working fluid is helium. So, choice of helium is very natural because it is inert gas, and we are actually integrating with nuclear fuel. So, that is the choice that helium should be the working fluid. Now, when we are using this, we have this helium turbine and helium compressor. So, this is the complete unit is gets power, and we get the power from the gas turbine unit, and here we do not have exhaust because the helium is getting recirculated in the cycle, but what we normally do is that the heat exchange in a feed water heater. So, that is allowed from the gas turbine unit to the steam turbine unit, and from the steam turbine unit we do not have here, because here if you look at this is the gas turbine unit and this side we have steam turbine unit or steam power system. But how these two cycles are combined? They are combined through feed water heater. Normally steam power systems use the feed water heater for its applications. So, this feed water, the necessary energy is being supplied to the feed water to the steam power unit. So, the combination or connecting point between this gas turbine unit and steam power system is the feed water heater. Now, some workable numbers, what we can see is that we have helium normally operates at very high temperature 800 degree centigrades. So, it can expand and generate the power through gas turbine unit. Then we can couple this to this steam cycle through this feed water heater. So, the heat generated from this STGR is completely used from the both cycles, and heat rejected is only in the condenser. So, heat rejection point, that is Q out, is only in the point of contact which is from the condenser. So, that way what we see here, exit point is only one, but all the resources are getting utilized within this combined cycle mode. So, this particular arrangement we call this as a combined cycle with nuclear gas turbine and fossil fuel based fired steam turbine unit. So, next viewpoint that I want to emphasize. So, this is all about the versatile ways of applications of gas turbine units which can be integrated to any kind of power generation unit. And now, to see the justification for this integration for thermodynamic operations through combined mode, we also need to revisit some of the basic concepts that why we are going for such kind of combined mode operations. So, with the thermodynamic viewpoint, because the combined mode increase the complexity of the systems. So, increase the also infrastructure high cost. So, that analysis has to be justified technically. So, a thermodynamic viewpoint for this power plant system is that we must perform the energy auditing. So, one such energy auditing could be energy analysis and exergy analysis. So, for that reasons I have given a simple example as a case study. So, what we do see here, we have a simple gas turbine unit and we have also a vapor cycle unit or steam power unit, and the coupling point between them is a what we call as heat recovery steam exchanger. So, what happens is that so they operate and each unit as is operating with their individual limits and they have their own efficiency, that means isentropic efficiency for the compressor and isentropic efficiency of the condenser. Then the energy that gets added is from the fuel, that is Q in comes in, and exhaust that comes out from the turbine is getting utilized in the heat recovery unit. So, essentially the heat input that comes to the vapor cycle is through exhaust from the turbine. So, as a realistic number different, as you can see, the peak temperature for gas turbine is 1400 degree Kelvin, whereas for steam cycle T7, that is maximum temperature is 400 degree centigrades. So, that way we can think that exhaust has sufficient energy to power the vapor cycle. And of course, for this steam cycle also turbine has its own efficiency 90% and they will have a pump efficiency, and finally, when the exhaust goes out to the atmosphere, you can see here the pressure is close to 1000 kilopascal, which is close to atmospheric pressure. Temperature is little bit high 400 degree centigrade, just if you say 300 degree Kelvin is the normal atmospheric temperature, it is 100 little bit higher, but that is a unavoidable loss, that is due to irreversibility. Now, what basic assumption for this simple unit for our energy and exergy analysis is that we need to do them in component wise for gas cycle and steam cycle. Second thing is that each unit can be analyzed as a control volume operating at steady state with negligible drop in kinetic and potential energy, no pressure drop in the combustion, heat recovery systems and condenser. And for gas turbine unit, we will use this air standard cycle for gas turbine units, and for vapor cycle we will think about Rankine cycle unit. So, for that reasons a case study which is prepared based on these thermodynamic cycles which has been noted here is that a combined cycle has a net power output of 45 megawatt, air enters the compressor at certain conditions. So, basically both the units will have combined unit, we have 45 megawatt power which they produce. The inlet conditions of air for the compressor in the gas turbine unit is given and maximum pressure is given, isentropic efficiency for compressor and turbine is also given, even turbine inlet conditions are also specified, and the interconnecting unit is the heat recovery steam generator, and that finally discharges necessary heat input for the steam cycle. So, steam cycle has their own numbers like isentropic efficiency for turbine and pump. So, what we need to find out is that What our main objective is that with the basic data points, we have to individually calculate the steam cycle unit and gas cycle unit, which has been emphasized in our previous lectures. So, normally when you say steam cycles or vapor cycles, we used to look into modified Rankine cycle, and necessary steam data we can obtain it from the steam tables, and based on that we can find out the enthalpies at various locations for the vapor cycle unit. And for gas turbine units, we need to look into air data, because it is we have to assume it as a air standard cycle. So, based on this air standard cycle, we can think of modified Brayton cycle, or in fact ideal Brayton cycle. Of course, it should be a non-ideal Brayton cycle, because we have efficiencies into picture. So, with this analysis we can find out the enthalpies at each cardinal point. So, those part I am skipping, but what we essentially require, we require the thermodynamic data points at each locations, like 1, 2, 3, 4 for gas turbine unit and for the steam power unit. So, those numbers I am just noting down here to solve this problem, because we need to find out the mass flow rate of air and steam, net power developed, that is first part, because when you operate in a combined mode. Second thing, whether that combined cycle is justified or not, we need to perform the exergy analysis, and the exergy that comes into the system is through this in this combustor. So, exergy entry to the combined system is through this condenser, but exergy which is lost, that is in the condenser, it is in the exhaust and other unit, like since these components they operate at different units, that means exergy lost in the turbine for the steam turbine, exergy lost in the gas turbine, exergy lost in the heat recovery unit, all these things has to be recalculated. Then we need to perform the exergy balance, or the kind of exergy which is lost, and with these numbers we can predict whether the justification of steam and gas turbine unit is verified or not. So, to solve this problem, the first step is to obtain the data points for steam and gas cycle. So, here I have just noting down the different state points for the gas turbine units and steam turbine units or steam cycle. So, what data we normally require is the enthalpy points and entropy points. So, we say state and enthalpy kilojoule per kg, and entropy, here we need to know absolute entropy, that is kilojoule per kg Kelvin, and this absolute entropy is a function of temperature that we can obtain from any thermodynamics books for air. For steam cycle, we have to use steam tables to calculate enthalpy and entropy, because we all know their conditions of operations, pressure and temperature, and pressure, either saturation pressure, temperature, whatever may be. So, based on that things we can find out this data table. So, typically for gas turbine units we have 1, 2, 3, 4 and 5, and their numbers are, I am just writing down 300.2, 1.702, state point 2, 669.8, 2.509 for entropy, 3, 1515.4 that is enthalpy, 3.362 entropy, 0.4 858 and entropy is 2.762, state point 5 401, 1.992, and for steam cycle we have points like 6, 7, 8, 9. So, these numbers are being noted here: 184 enthalpy, 0.5975 entropy, state 7 3138.3, 6.3634 that is entropy, and state 8 2104.7, 6.7282 that is entropy, state 9 173.9 and 0.5926. So, these data points are obtained by separate analysis for gas turbine and for steam turbine unit. For steam cycle we use steam table, for gas turbine cycle you use the property data for air. So, having said this, we need to perform first thing is energy analysis. So, for energy analysis we need to know that how the entire energy comes to the steam power unit. So, for that we have heat recovery steam exchanger or steam generator. So, here what we can see here, your gas that comes is mg, steam vapor that enters is m dot v. So, this is your mass from the gas turbine gas unit and this is for vapor unit. So, if you say this energy balance, so mg dot into H4 minus H5, that is heat extracted from the gas that is fed by to the steam unit, that is m dot v into H6 minus H7. So, this will give you a ratio of m dot v by m dot g as H4 minus H5 divided by H7 minus H6. With the data which was been supplied, we can find out it is 1547. So, now what is the power that goes as a W dot gas? So, we say W dot gas is equal to m dot g into turbine work minus compressor work for the gas turbine unit, H3 minus H4 minus H2 minus H1, and W dot steam is equal to m dot v into H7 minus H8 minus H6 minus H9, turbine work minus compressor work. And what has been given is that W dot gas plus W dot steam is equal to 45,000 kilojoule per second kilowatt. So, we have two equations now. So, combining these two and solve for, because we have two equations, all the data points are known, unknowns are m dot v and m dot g. So, two equations and two unknowns. So, we can find out what is m dot g, that is equal to 100.9 kg per second. So, gas flow rate, and vapor flow rate will be 15.6 kg per second. So, after substituting we can find out what is W dot gas, that is 29 megawatt, and W dot steam, that is equal to 16 megawatt, and Q in is equal to m dot g into H3 minus H2, that is the heat that is supplied at this point, that is at the combustor unit. So, it is 85.3 megawatt, and you can find out cycle efficiency as W dot net by Q dot in. W dot net is 45 megawatt divided by 85.3. So, this is 52.8%. So, what we observe here, if you look at closely for only gas turbine unit or steam turbine unit separate operations, normally efficiency of gas turbine unit falls in the range of 40%, and even for steam unit it is in the range of 35%. But when you combine them with this given data, a simple analysis will tells you that efficiency is enhanced. Of course, power we can obtain from the both units. So, that way the energy analysis says that combination of steam and gas turbine units is essentially justified. This is about first law and second law analysis. Then we need to see whether exergy analysis is further justified or not, because that is the essentially backbone, because we need to know, because this exhaust that goes to atmosphere and atmospheric conditions is P naught, which is 1 atmosphere, and T naught is which is 300 Kelvin, that is a dead state. Now, when you perform this exergy analysis, then picture will be more clear. So, to do that, first thing we need to find out where are the point of entry for exergy entering into the systems and where are the points of exergy that goes out, and other points is that where are the points where exergy is lost. First thing is that exergy entry is to the combustor, that is exergy in, and exergy that goes out is out through this exhaust from the gas turbine. Other point of exergy out is the condenser, steam condenser. So, we need to calculate that. Then also exergy turbine pumps, they operate their efficiency. So, there we say it is a exergy lost, which is not recoverable. So, we need to calculate them one by one. First, combustor. So, here we say increase in the exergy. That is nothing but E dot F3 minus E dot F2, and it is operating with gas, which is mg dot, that is mg dot into H3 minus H2. Here we have to recall the expression of exergy, where keeping surrounding into picture, and since this is, we need to find out this entropy for the gas with respect to absolute entropy mode. So, that is becomes m dot g into H3 minus H2, that is equal to T0 into S0 3 minus S0 2 minus R ln P3 by P2. So, this there is no pressure change here. So, this term goes to 0, and ultimately what we arrive at is, and of course, T0 is equal to 300 Kelvin. So, what we arrive at is that E dot F3 minus E dot F2 is equal to 59.5 megawatt. Please recall that is the this number, because that is the entry. Now, exergy that is carried out by exhaust flow. So, that is nothing but E dot F5 minus E dot F1, that is inlet and exhaust. That also you can write in this form, that is m dot g into H5 minus H1 minus T0 into S5 0 minus S1 0 minus R ln P5 by P1. So, this term vanishes, this goes to 0 because P5 and P1 they are equal atmospheric. So, we say E dot F5 minus E dot F1 is equal to 1.4 megawatt. So, this turns out to be about, if you divide by 1.4 by 59.5. So, this turns out to be 2.3%. So, this is quite justified because we are not losing too many exergy. Then we move on to condenser. So, condenser point is this point. So, we say E dot F8 minus E dot F9, that is m dot V H8 minus H9. So, you have to use the data from the steam unit T0 S8 minus S9. So, looking at the number, this will be E dot F8 minus E dot F9 would be 1.4 megawatt. So, this is again close to 2.3%. Then exergy destruction. So, this happens at component wise, like turbine, compressor, air turbine, air compressor, steam turbine, pump. So, we say air turbine. So, here we write this exergy destruction E g T is nothing but m dot for gas turbine unit, that is S4 minus S3 into T0. So, this is the exergy destruction term. So, we say exergy destruction for gas turbine ED gas turbine unit. So, this number is m dot G T0 into S4 0 minus S3 0 minus R ln P4 by P3. So, here pressure terms cannot be neglected because turbines both ends will have different pressures. So, using this we say exergy destruction in the gas turbine is 3.42 megawatt. So, this number is close to 5.75%. Similarly, air compressor, we write E dot D, that is exergy destruction gas compressor is m dot G T0. Here the numbers will be S2 0 minus S1 0 minus R ln P2 by P1. So, we say E dot D gas compressor. So, this data will give you 2.8 megawatt. So, this turns out to be in the range of 4.7%. Then pump, okay, steam turbine. So, we say exergy destruction for steam turbine unit is m dot V, because here we have absolute term or actual term, that is S8 minus S9, it is 1.7 megawatt. So, this ratio is close to 2.8% if you divide by the 59.8. Then pump. So, pump, that is exergy destruction for pump, steam turbine pump, m dot V T0 H6 minus H9. So, this is 0.02 megawatt. So, this number is much less than 1%. So, that means pump will have negligible exergy loss. And heat recovery steam generator, heat recovery steam exchanger, that is E dot D is equal to T0. Here we have both the units like m dot G, that from gas mode, S5 minus S4, and m dot B, that is for steam mode, that is S7 minus S6. So, this number is 3.7 megawatt, it's close to 6.2%. So, what we observed here, wherever the exergy that comes in is from the combustor, it is almost getting utilized, and loss at all points is quite minimal, which is falls in the range of maximum 6%. So, exergy analysis also is quite justified, because second law also tells some exergy is always destroyed, we cannot recover it completely. However, for this present problem, it is quite justified that, in fact, exergy analysis justifies this fact. These numbers are quite realistic, and based on which we can take a decision, appropriate decision of combining a steam power unit with a gas power unit. So, energy analysis is quite justified, because cycle efficiency of combined mode is always higher. Exergy analysis also tells us that the loss of exergy at each component wise is quite minimal, which is close to less than 6%. So, hence combined mode of gas turbine operations is quite possible, and with respect to steam unit. So, this is all about the combined power cycle. With this I conclude. Thank you for your attention.